Hello, and this time I want to go through a few examples of the use of these phasor techniques to analyse AC circuits using Ohm's law and the AC equivalents to Ohm's law and Kirchhoff's laws. You'll be getting a lot of practice on these types of problems soon. Quick reminder of the results that we are going to need to know and are worth learning. The complex impedance of a capacitor is 1 over j omega c. The complex impedance of an inductor is j omega L. And as we've seen, these complex impedances are the ratio of the phasor representation of the voltage across the component to the phasor representation of the current flowing through the component. First problem, we have an ammeter telling us that the phasor representation of the current flowing through the ammeter is 143.2 milliamps at a phase angle of 180 degrees. And that current is flowing through an inductor. What would the voltage across the inductor have to be? This is just an application of the AC version of Ohm's law. The phasor representation of the voltage is equal to the phasor representation of the current times the complex impedance. The complex impedance of an inductor is j omega L. So in order to do this problem, we're going to need to know what the value of omega is. The frequency is usually specified in terms of hertz. So supposing the frequency here was 10 kilohertz. That would mean that the angular frequency would be 10 kilohertz times 2 times pi, because that's how you convert from a frequency in hertz to a frequency in radians per second, multiplied by 2 pi. We know the phasor representation of the current. That's what the ammeter is telling us. So the phasor representation of the voltage source must be the phasor representation of the current, 143.2 milli at a phase angle of 180 degrees, multiplied by the complex impedance of the inductor, which is J times omega times L. L, in this case, 22 millihenries. And we have to do some complex algebra, and it really helps if you have a calculator able to do complex numbers. And for the most part, you will have. In this case, we just have to do 143.2 milli at 180 degrees multiplied by j times 2 times pi times, in this case, 10 kilohertz times 22 millihenries gives you an answer 198 at minus 90 degrees. So, in terms of the phasor representation, that would be down here at a phase angle of minus 90 degrees. The distance from the origin is 198. So if I was going to represent this voltage as a real oscillating voltage, I would write that as the voltage as a function of time is amplitude 198 times cosine omega t minus 90 degrees, or in radians pi over 2, and that's equal to 198 sine omega t, which is probably how I would write it because it's a bit neater. Okay, next one. Here we're given the current flowing through this capacitor and asked to work out the voltage across it. So, very similar problem to the last one. We know the current, phasor representation 9.8. This time it's at a positive angle of 90 degrees, so I could just write that as 9.8j, since on an argan diagram it would be up here. 9.8, that's the distance from the origin, phase angle 90 degrees puts it up there at 9.8j. Multiply that phasor representation of the current by the complex impedance of the component, which in this case is 1 over j omega c, because that's the complex impedance of a capacitor, and the result will be the phasor representation of the voltage across the capacitor. Here, quite conveniently, those two j's cancel, so the result is going to be real. 9.8 divided by omega c. And I can work that out. If the frequency is again 10 kilohertz, that would be 9.8 divided by 2 times pi times 10 kilohertz times c, which in this case is 220 nanofarads. That just gives you 709. So the phasor representing the voltage across this capacitor is just the real number 709, which means the time domain waveform that would appear across that voltmeter would be 709 times cosine omega t. Let's try one about Kirchhoff's laws. Okay, here we have an application of Kirchhoff's voltage law. Kirchhoff's voltage law will tell you that the total sum of the voltage differences around a closed loop is 0, or alternatively, the total sum of the voltage differences between 2 points in a circuit is independent of the route taken. So in this case, going up the left-hand leg from the bottom to the top would be the unknown voltage measured by the voltmeter plus phasor representation of the voltage here, which is 1.4 millivolts at minus 90 degrees. And that must be equal to the sum of these two phasor representations. 600 microvolts at 90 degrees and 1.2 millivolts at 135 degrees. Once again, it's just a bit of maths. We need to take 600 microvolts at 90 degrees, add 1.2 millivolts at 135 degrees, and subtract 1.4 millivolts at minus 90 degrees. That would give us 600 micro at 90 plus 1.2 milli at 135 minus 1.4 milli at minus 90, which is 3.03 millivolts at 106 degrees. So that's the phasor representation of the voltage across this voltmeter. And once again, if I wanted to express that as a time domain waveform, I would just write it as 3.03 cosine omega t plus the equivalent of 106 in radians, which would be, let's see, 106 divided by 180 times pi, or about 1.85 radians. The final one I'll look at is an application of Kirchhoff's current law. And if we look at this node in the circuit here, we can see that the total current flowing in is an oscillating current represented by the phasor 10 nanoamps at 0 degrees, or just 10 nano, an oscillating current represented by the phasor 100 nanoamps at 135 degrees, and the current flowing out of this node is the current flowing through the voltmeter. Well, the total current flowing out must be equal to the total current flowing in, so the current through the voltmeter must just be the sum of these two. So, once again, a bit of complex maths required. This time 10 nano plus 100 nano at 135 degrees is 9.32 times 10 to the power of minus 8 at 131 degrees. And I would probably normally write that as 93.2 nanoamps at 131 degrees. And once again, if I wanted to express that in terms of a time domain waveform, I would just take that phasor, convert it back into the time domain waveform which it represents, and that would give me 93.2 nanoamps times cosine of omega t plus 131 degrees expressed in radians, which is 131 divided by 180 times pi, or 2.286 rather, radians. That would be the current as a function of time, the real current. And that's it. With a bit of practice, it's actually quite straightforward, provided you have a calculator that's good at doing complex numbers. In the quiz app, you do. In the exam, you may not, so it'd be a good idea to get some practice doing this kind of manipulation of complex numbers, adding them up, dividing them, and so on, with whatever calculator you have. Next time, we'll look at some problems in potential and current dividers.